Happy New Year, everyone, and I hope you are all well. And I hope that you're going to engage over these next 2 weeks so we can keep up the progress. I see no reason why we need to slow down. We're going to keep going. And as you've seen in my email, hopefully, I want to keep in touch with you using whatever method you prefer. So, yeah, make sure you are feeding back to me how well you're getting on. So at the end of last term, using a combination of lessons and videos, I think for most people, we had one lesson on proof in class and then one on video, although some of you were at home for both of those. We looked at a revision of GCSE proof. We looked at a method of proof called proof by deduction. We looked at proving identities, that's statements with a triple equal sign that are always true, where you lock one side and fiddle around with the other side. And then we also looked at proof by exhaustion. That was in the last video before Christmas. And today I just want to talk about the final easiest method of proof that we come across this year, and that's disproving something, not proving it, but disproving it by a counterexample. Before we get into that, though, let's just do one example of proof by deduction and one example of proof by exhaustion, just to get up to speed. So here we go. This is a proof by deduction question, and it should be familiar to you because it comes from that past paper that I asked you to have a look at over Christmas. I think it was question 8A. It's very much like the ones we'd done in class and the ones I did on the video. They said always positive, which maybe sort of confused you. What they're asking you to show is that that means it's greater than 0. Is 0 positive? Well, we're going to show it's greater than. We don't have to worry about greater than or equal to. And if you remember with proof by deduction, it's about rough working first, followed by your actual solution. One thing you mustn't do is start with the thing you are trying to prove. You mustn't just start with that statement. You've got to end up with that statement. But in our rough working, I'm going to start with the statement. And the way I do it, which is different to the way the mark scheme did it, I do this by completing the square. So I say, okay, if I want to complete the square with more than 1x squared, shovel the 4 out to one side, take out the 3. So this was a nasty one, but still positive. Then just complete the square for that bit. So that's 1x, so we'll have x minus a half in the bracket, minus that number squared. Multiply out the bracket. Remember, we can't break into the squared bracket, but 3 times a quarter is 3/4. And then minus 3/4 plus 4, you end up with plus 3 1/4. I'm going to write that as 3.25. Now, I know that anything squared is always greater than or equal to 0. So 3 times that will always be greater than or equal to 0. Add 3.25 on. It's always going to be greater than 0. It's always going to be positive. So by completing the square, I've done what I've been asked to do. I've just got to summarise it now. So I'm going to start by saying, right, this is greater than or equal to 0. Okay, that's something squared, and I know whether you square a positive or a negative number, the answer is always positive. If 0 is the number you start with, then it'll be 0. That's why I've got the extra line there. So 3 lots of that will also be greater than or equal to 0. And if you add 3.25, and actually I don't need that anymore, do I? Because now, if this was 0, this is going to be greater than 0. And the last step is just to say, right, that this is the same as this. So I'm just going to write I might put a therefore in, just to sort of link those two, or you could write which is the same as that. So I've proved that that is always greater than 0, which is the same as saying it's always positive. So I am there. So that was proof by deduction, and that was that question from the past paper, the practice paper. And it was a nasty one. It's nasty because of the numbers. They're not nice, easy numbers, but the process is the same. I know they used discriminant in the question. They used the discriminant for this to show that it has no roots, and that means the graph of that doesn't cross the x-axis, and therefore it's always positive, and that's a perfectly valid explanation as well. So let's have a look at a proof by exhaustion. If you remember, proof by exhaustion is where you try all the possible different sorts of number, and sometimes it's a limited range of actual values, and then we also did questions where you tried odd numbers and you tried even numbers, and all numbers are either odd or even, so that covered all our bases. Here's one which threw me completely when I saw this in the textbook, because if you use odd and even numbers, it doesn't help you at all. And the clue here is that there are 3 cases, so I need to try 3 different sorts of number. And that leads us to the conclusion that we need to try either multiples of 3, which I'm going to describe as 3n, or numbers that are 1 bigger than a multiple of 3. So that would be, or numbers which are either 2 bigger than a multiple of 3 or 1 smaller than a multiple of 3. And this is about cube numbers, so we've got to show that if I cube those numbers, I get either that, that, or that. Now, that step, how did I know it was multiples of 3? Well, I'll be honest with you, I didn't until I looked in the solutions, but the clue was that if I came across this again, I would know 3 different options must mean something to do with multiples of 3. Have I covered all my bases? Is every number in the world either a multiple of 3, 1 bigger or 1 smaller? Hopefully you can see that it is. If you count through the numbers, you get to a number like 9, which is a multiple of 3. 1 bigger than that is 10, 1 smaller than that is 8, and then the next number is 11, which is 1 smaller than 12, and so yeah, I've covered all my possibilities here. Any number is either a multiple of 3, 1 bigger or 1 smaller than a multiple of 3. Now, if I multiply that out, so that's 3n times 3n times 3n, I get 3 times 3 times 3, 27n cubed. Remember, if I want to prove something's a multiple of 9, I just have to write it as 9 times something. Well, that's 9 lots of 3n cubed, which is a multiple of 9 as required. So I've proved that if you start with a multiple of 3 and cube it, you get a multiple of 9. What about if you start with a number that's 1 bigger? So you've got to do and remember how we do that? Multiply those 2 out first and then take your answer and multiply by that. Press pause, have a go. Okay, so grid it out again. I got this. Now if I ignore the 1, I can prove that this is a multiple of 9 because it's 9 lots of 3n cubed plus 3n squared plus n. So that plus 1 is 1 more than a multiple of 9, which is 1 more than a multiple of 9, as required. So I've shown that if you start with a multiple of 3 and cube it, you get a multiple of 9. If you start with a number that's 1 bigger than a multiple of 9, you get, 1 bigger than a multiple of 3, you get an answer which is 1 bigger than a multiple of 9. So I've found that happens, and that happens. So what about if I start with a number that's 1 less? Well, I did that one for you. You end up with, looks very similar to that, and that's 1 less than a multiple of 9. as required. So by trying these three numbers, which cover all eventualities, I've shown that you always get one of those three options. So that was proof by exhaustion. So lastly with proof, what about disprove by counterexample? So prove that the sum of two consecutive prime numbers is not always even. So what I'm being asked to do here is not prove something, I'm being asked to prove that something is not true. I'm being asked to disprove it. And if I can find one example that doesn't work, then I can say, well, yes, it's not going to work all the time then. So all I'm looking for is one example that doesn't work. And if I find one example that doesn't work, I can say I can't say it's always going to work. So consecutive prime numbers. So here we go. Here are my prime numbers: 2, 3, 5, 7, not 9, 11, 13. The sum of two consecutive prime numbers. So if I add together two consecutive prime numbers, like 5 and 7, I get 12, which is even. So that doesn't help me. I'm trying to find an example that doesn't work. But hopefully you can see if I add 2 to any of them, sorry, it's got to be consecutive, so I can only add 2 to 3. That doesn't work. So that one doesn't help me. But because I can find an example that doesn't work, that's what I've been asked to do. So I'm not being asked to prove something, I'm being asked to disprove it. I'm being asked to prove that this is not true. You don't always get even numbers when you add two consecutive prime numbers. And it can be worded as a disproof. So can we disprove the fact that integers always have an even number of factors? So if I take a number like 12, the factors of 12, well, I always think of them as coming in pairs because they're numbers you multiply together to make 12. So 1 times 12, 2 times 6, 3 times 4. So 6 factors, that's an even number of factors. Can I think of a number which doesn't have an even number of factors? Hopefully you're all shouting at the screen. Square numbers, yeah. If you think about a number like 16, you've got 1 times 16, 2 times 8, and then 4 times 4. A number multiplied by itself. So actually, how many factors does 16 have? It has 1, 2, 3. It's the same number. 4, 5. So 16 has an even number of has an odd number of factors. So 12 doesn't disprove it, but 16 has 5 factors, which are 1, 2, 4, 8, and 16. So we have found our example. And then show by means of a counterexample that this 2n squared minus 6n plus 1 is not positive for all values of n. So what we've got to do is to find one value of n where if we plug it into that, you don't get a positive answer. Now, you can either do this manually, try different numbers, or you could use the table function on your calculator and just try a range of numbers. All we're looking for is one value which gives you a negative answer to this. So I'm going to pause at that point, see if you can find such a value, either manually or using a calculator. So I typed it in to my calculator. Obviously, the calculator thinks in terms of x rather than n, but there we go, typed in the same one. Remember, you then go to set. So I thought, right, I'll try numbers from minus 5 to 5, going up in ones, because it says integers, definitely says integers. And I go to table. So when n is minus 5, you get a positive answer, 81. Minus 4, positive answer. When n is 1, I get a negative answer. And was it just 1? No, 2 as well. So 1 and 2 were values you could have used. So how am I going to show that? So when n is 1, I'm going to do my exaggerated substituting method. So that's 2 minus 6 plus 1 equals minus 3. As required. So all you're looking for in disproof by counterexample, questions are one example that shows that it doesn't always work. Now, disproof by counterexample questions often come alongside another sort of proof. And very often, in the few years we've had exams, they come with a question like this, where you're first asked to identify an error that someone else has made. So here is, in part A proof by deduction question. We've got to show that this is less than this for all values of x. And the person doing this has, they've started right, they haven't started with that, they've finished with that, although they've written it the other way around. So they've done that bit right. And they started by expanding that, so 1 plus x squared is 1 plus 2x plus x squared. And then they've compared, so they've said that is 1 plus 2x plus x squared. And they've compared it with this side, 1 plus x squared. And they've said that this has got to be bigger than this, because it's got the 2x in there. And therefore, the proof statement is correct. Can you see the error they've made? Well, this is only true if x is positive, because if x is negative, then this would be negative, so actually this side would be smaller than this side. So the error they've made is the student has assumed x is positive, has assumed x is positive. Now, can we provide a counter example to show the statement isn't true? So what we're looking for is one value of x that means that that doesn't work. Okay? And we've already got a bit of a clue here, because the person who's proved it has proved that it does work if x is positive. So I'm going to try x is minus 1. If x is minus 1, I've got 1 plus minus 1 squared. And I've got 1 plus minus 1 all squared. That's what these two things are equal to. So that's plus 1, so I get 2. And that's 0. 0 squared is 0. 2 is not less than. 2 is greater than 0. So I've disproved it by finding an example that doesn't work. This doesn't work if x is equal to minus 1. So in the textbook, on page 153, there are a couple of questions, question 6 and question 10, which are very much like this one. You start by identifying an error, and you don't have to redo the proof. You've just got to say what the person who did it did wrong, and then you've got a counterexample question. So although they look quite nasty, there's very little work involved. So have a go at those two questions, and we'll pick up with this in tomorrow's video. So this is Tuesday's video, so you'll get another video this week on Wednesday, and then a final video for the week on Thursday, and then in Friday's lesson I will set you some homework that you can do in that lesson time.